You are about to embark on a flight through and around Lake Tahoe, viewing the landscape as scientists. Lake Tahoe has undergone many forces. Human activities, including urbanization, the introduction of invasive species, and climate change, are recent. Others, like plate tectonics and fault movements, volcanoes and glaciers, have been occurring for millions of years. This journey provides the underlying natural history of the basin for a better understanding of current challenges.
Immediately east of the Sierra Nevada, arrows indicate a zone of shear where California is tearing away from Nevada. The Lake Tahoe Basin is being pulled apart by movements of the Earth's crust. The Tahoe landscape was formed and continues to be formed by powerful tectonic forces.
Lake Tahoe is surrounded by mountains that form a bowl-like basin or watershed. Snow and rain falling within the watershed eventually reach the lake by way of streams and groundwater. The land portion of the watershed is only a little bigger than the lake itself. That's one of the reasons Lake Tahoe is naturally and spectacularly clear.
This three-dimensional image is made from measurements of the land elevation, the lake basin depth, and satellite images. The vertical scale is exaggerated so that features can be seen more easily. The landscape was formed by movement along several major faults. Earthquakes helped shape the basin over the last 2 to 3 million years. Erosion and glaciation added finishing touches, helping to conceal the faults. The West Tahoe Fault is the longest fault, and it's responsible for most of the vertical offset that occurred in the lake basin. The last major earthquake on this fault took place over 4,000 years ago. Geologists say this fault is due for another earthquake.
The Truckee River near Tahoe City is the only outflow from Lake Tahoe. The dam at the outlet was completed in 1913 to hold back an extra 6 feet of water for use downstream. During extremely wet years, it is a challenge to release sufficient water to prevent overtopping and catastrophic flooding. During droughts, the lake level falls lower than the natural rim at the dam, and no water flows into the Truckee River until rain and snowmelt refill the lake above the rim. Researchers work out of the UC Davis Field Station in Tahoe City. Because of the extent of the shallow Tahoe City shelf, these researchers travel several miles aboard research vessels to collect water samples and deploy scientific instruments in deep water. Secchi depth readings and other measurements have documented a loss of lake clarity since the 1960s. Samples taken have also shown changes in the species of the lake's algae and microscopic animals, high concentrations of microplastics, and the impacts of smoke and ash from wildfires.
We are now looking to the northwest, where ancient volcanic eruptions dammed the Truckee River. The result was lake levels much higher than we see today. The volcanic soils in the northwest are naturally rich in phosphorus, an important nutrient for algal growth that supports life in the lake. The steep underwater cliff east of State Line Point is the State Line Fault. This underwater cliff face descends to the deepest part of the lake, 1,645 feet below the surface. Imagine swimming over this edge and looking down into the darkness. The Incline Village Fault extends from the land to the depths of the lake. Sound waves reflected from the lake bed sediment show that the east side of the fault has slipped downward. The last big earthquake here was about 500 years ago.
The east side of the lake receives half the precipitation that falls on the west side due to the rain shadow effect. The Carson Range, east of the lake, is almost entirely granitic rock. The clarity of Lake Tahoe is partially attributed to the amount of granitic rock surrounding the lake. Weathered granite is low in nutrients. Moving along the east shore and Carson Range, we can see the Flume Trail. Today, mountain bikers enjoy this spectacular trail that was cut into the granite to carry water from Marlette Lake to Virginia City.
In the late 1800s, most of the trees in the Tahoe Basin were cut down and transported to the silver mines around Virginia City. The mines of the Comstock era were called the Tomb of the Sierra Forests. Accelerated erosion on barren slopes reduced Tahoe's famous clarity for many decades. Eventually, the second growth forest helped slow the erosion, and lake clarity was naturally restored.
Natural caves and cave rock were cut by wave action thousands of years ago when the lake level was much higher. Similar caves are found in Eagle Rock on the west side of the lake. Wave action also cuts terraces into the lake sediment. Ancient terraces mark the changes in lake elevation due to movement along faults. Caves and terraces on the west side are higher relative to caves and terraces of the same age on the east side. This confirms the long-term trends of east side downfault movements in the basin.
The southeast corner of the lake was invaded by non-native Asian clams in 2002. Since then, they have spread considerably along the full extent of the South Shore. Smaller populations also exist on the East Shore and, in time, may spread further. Asian clams occur in dense colonies on the lake bed, as many as 2,000 per square meter. Their excretions concentrate nutrients that stimulate algal blooms. These algae, or metaphyton, often wash up on beaches and create smelly, decomposing mats during summer. Invasive species introductions are changing the underwater landscape and lake shoreline in detrimental ways. UC Davis researchers are partnering with lake managers to understand and control the spread of non-native species and mitigate their impacts.
The watersheds of the South Shore are the largest and the most urbanized in the basin. Building, road, and airport construction and modification of natural stream channels have significantly altered this region. Stormwater runoff from parking lots and roads carries polluted water into the lake. Urbanized land makes up only 11% of the basin, but contributes nearly 3/4 of the fine particle pollution. Fine particles carried into the lake are primarily responsible for the loss of clarity. About 1/3 of the stream inflow and most of the urban runoff comes from the upper Truckee River watershed. Landowners in the basin are required to minimize the amount of sediment and fine particles that flow from their property by following best management practices, or BMPs. Stream and wetland restoration also helps reduce sediment and nutrients by trapping them before they reach the lake. While the upper Truckee River will never return to its pre-development condition, restoration efforts aim to improve how the watershed functions. The area that is now the Tahoe Keys used to be a natural sediment-trapping wetland or marsh. That marsh was originally one of the largest in the Sierra Nevada. A wetland is an amazingly effective water filter, settling the sediment and absorbing the nutrients. That filtration capacity is lost every time we lose a wetland. Restoration efforts and small constructed wetlands attempt to regain what was lost. All remaining wetlands in the basin are now protected from development.
The shallow, warm channels of the Tahoe Keys provide fertile habitat for non-native species to flourish. Aquatic plants like Eurasian water milfoil and curly-leaf pondweed provide shelter for warm water fishes, such as largemouth bass and bluegill. These non-native species have made the Tahoe Keys their home. From the Keys, they have migrated, transforming a localized problem into one that is impacting the entire lake. Warming from climate change will likely accelerate this colonization by creating conditions that are ever more welcoming to new invaders. Warmer water temperatures also increase the possibility of harmful algal blooms in the lake, making them a concern that will require monitoring in the future.
A wildfire raged in the Angora Ridge area of Lake Tahoe in 2007, burning over 3,000 acres and destroying 250 homes. 14 years later, the Caldor mega wildfire burned more than 200,000 acres near South Lake Tahoe, with 10,000 acres burned within the Tahoe Basin. Had it not been for forest thinning and prescribed burns, the Caldor fire could have destroyed much of the South Shore. Wildfire is a major concern in the Tahoe Basin because after the Comstock-era logging, the second growth forest regrew thickly under a management policy of fire suppression. Now it is accepted that forest thinning, prescribed burns, and defensible space around fire-hardened buildings are necessary for forest health and to protect life and property.
Angora Ridge was formed by glaciers. Glaciers are massive, slow-moving rivers of ice, hundreds of feet deep that gouge out the landscape. Rocks in their path are incorporated and carried down slow, piling them into giant ridges or moraines. After glaciers retreat, U-shaped valleys and moraines are left behind. Lateral moraines are created along the sides of a glacier's path, and terminal moraines mark the end of the glacier's progression. The height of the Angora Ridge lateral moraine indicates the height of the glaciers that formed it. Scars in bare granite illustrate the power of ice pushing down from above. At least 3 major glacial episodes in the last 200,000 years caused the snowpack to last through the summers. Ice blanketed the mountains for thousands of years, shaping the land with glacial features.
In the southwest corner of the basin, Fallen Leaf Lake sits within a glacially carved canyon. Dead trees standing underwater in Fallen Leaf Lake and in Lake Tahoe off Baldwin Beach show that forests grew here when the water level in each lake was much lower. Shallows now covered by water were once covered by trees, indicating climates much drier than modern times. What do you think the Lake Tahoe forest might look like in the future as a result of climate change? More trees? Less trees? Or just different trees?
Taylor Creek flows at a Fallen Leaf Lake. Non-native kokanee salmon spawn there in the fall, attracting both onlookers and bears. Kokanee salmon were accidentally introduced to Lake Tahoe in the 20th century and have thrived. The kokanee have become a colorful part of the Tahoe scene.
Moving north, we see Cascade Lake and Emerald Bay, and a ridge separating them. When you drive along the highway atop that ridge, you are riding the backbone of the lateral moraine left behind by Ice Age glaciers thousands of years ago. Glaciers reached the edge of Lake Tahoe but advanced no further. A terminal moraine was deposited at the end of the glacier's path. Can you see the underwater terminal moraine at the mouth of Emerald Bay?
The spectacular Rubicon Wall is the underwater portion of the West Tahoe Fault. Above the surface, it makes up the tallest cliff along the West Tahoe Fault at D.L. Bliss State Park. The glaciers of the southwest shore spilled down the canyons from a large, thick ice field that covered the Sierra crest. Over the centuries, the glaciers surged and retreated like busy bulldozers piling up moraines. We've learned enough about glaciers now to recognize their telltale footprints. Can you find the lateral moraines flanking each U-shaped valley? The melt-off from the ice field carried sediment down the underwater cliff of the West Tahoe Fault, forming an alluvial fan. Do you see a cut across the alluvial fan? This is evidence of fault movement after the fan was deposited. The fault offset exceeds the height of a 3-story building.
As we approach Tahoe City, the landscape changes from granitic mountains scraped by glacial ice to volcanic mountains formed with fire. A large portion of the underwater shelf south of Tahoe City and west of the fault is missing. What happened here? All evidence indicates that an underwater landslide triggered by an earthquake occurred here about 17,000 years ago. Massive blocks of material protrude from the otherwise level lake bottom in the middle of the lake. They're made of the same material as the shelf. The longest of these blocks is almost a mile long, and another is nearly 500 feet tall. If the dimensions of the largest blocks are compared to the dimensions of the Golden Gate Bridge, you can see how gigantic these blocks truly are. Imagine the energy that must have been released when these huge slabs of sediment, hundreds of feet thick, slid several miles underwater across the lake bottom. The landslide raised a large destructive wave called a tsunami. Huge waves, hundreds of feet high, crashed over the shores all around the lake. Seismologists have developed a computer model that recreates what the actual event might have looked like. In this view, the simulation is superimposed on the satellite image of the basin today. The initial tsunami wave and its many reverberations, called seiche waves, spread the energy from the landslide around the lake. Within 20 minutes, the wave energy had largely dissipated, but in that time, nearly everything close to the lake was destroyed. Could such a catastrophe happen again? In the centuries to come, earthquakes and smaller underwater landslides could still produce destructive tsunamis.
We've seen evidence of extreme events, tectonic plate movement that caused earthquakes and formed steep cliffs, volcanic activity that dammed the Truckee River and raised lake levels, glaciation that gouged canyons and moved boulders, droughts that lasted for centuries, and an underwater landslide that caused a huge destructive tsunami.
The Tahoe Basin is an enduring record of all these events. It is also a record of the cumulative actions we take as individuals. What are we to learn from Lake Tahoe's past? And can we use those lessons to guide our actions today and in the future?
Here are some ideas to consider. If the lake can recover from the devastating tsunami and the Comstock logging, will it have the ability to withstand modern stressors, such as development and urbanization, the introduction of non-native species, and climate change-induced megafires? Will our responses to emerging threats be enough? Will the clarity and the ecosystem health of the lake recover within our lifetimes because we make the effort needed? Or after we are long gone because we could not live in harmony with nature? The decision is ours.
We see deeper into the scenery when we examine it through the eyes of science. Our appreciation of Lake Tahoe is enhanced by our greater understanding of its natural processes over the vast span of time.